All right, so here we are. This is Thursday, the 6th of May, 2021, Class 16, Packet 6. Today we'll talk about inclined planes. We'll start talking about elevators, and physicists love elevators. Einstein was probably the one who started the whole trend to loving elevators. And because Einstein was born in 1880, around there, and that's when Otis put out its first elevator. They had dumb waiters, but I mean, like the kind of modern lift, they called them, the kind of modern elevator you'd have today. That's when they first started coming out. So there was all the newfangled thing, right? Elevators. My question many years ago, I thought, well, what came first, the elevator or the skyscraper? And it turned out the skyscraper came first. I don't know, considered the skyscraper's 10 stories. So they had 10-story buildings way before they had elevators. And so you know who was on the 10th floor, right? It's the working class. It's the people that are working their butt off every day. They're the ones who are stuck on the 10th floor because no one wants to walk up 10 flights of stairs every day. So then they invented the elevator. They installed the elevators. The rich people kicked them out to the street, and they called that the penthouse suite. But I thought that was interesting. That's where the poor people lived, in the penthouse. All right, before elevators. So we're going to talk elevators today. Today I wasn't introducing books. I was introducing movies I had. I'm giving away all my DVD collection too of all my movies. And one of them was Rudy. And let me tell you the quick Rudy story. I told them. So you know Rudy, Rudy from Notre Dame, right? He was the basic guy, the scrub that did the lawn, and then they got him on the team, and he's always wanting to play football, and his dad, blah, blah, blah. So true story. So Rudy ends up playing in a game. Ara Parsegan, I think, was the coach. He plays in a game, and it's a great movie. It's just, if you haven't ever seen it, you got to watch it. Okay. So back about 15 years ago, Norman High got Rudy to come to Norman High to give a motivational speech. I mean, who else can give a motivational speech but Rudy, right? Rudy, the guy that, the actual guy that was in Rudy. So it was amazing. So we had for a month, we were preparing for this, get the kids all psyched up, and get a better light here. And so finally the day arrives, and everybody all for like a month's been going, Rudy, Rudy, Rudy. And the North Gym where Rudy was to speak was packed. We had adults and city people and students. There was no room even to sit. I had to sit down on the floor in an old folding chair. So Rudy finally comes out and gives his motivational speech. It was the worst motivational speech I'd ever heard. 45 minutes, him reading off a piece of paper, and he's not a very good reader, stumbling over his words right and left. He kept repeating the same stuff. Me, Rudy, at the White House. Me, Rudy. He's like, oh my God. Okay. So what I love about Norman High is the Norman High students, they give some clapping, but they were polite. They were civilized. And then Rudy got off. Everybody gave him a lot of applause. Unfortunately, I fell asleep. It was in the afternoon. It was hot. I was tired. I fell asleep, and everybody saw me because I'm on the floor and I'm like just snoring away. And so I got crap about that for like a month. Okay, so the last bit of that story. The next day, Rudy and his entourage goes to Norman North and does the same speech. Norman North students booed him off the stage. That's the difference between Norman High and Norman North. That's one of the differences. They booed him off the stage. Norman High would never do that. At least we wouldn't back then. Okay, so that's my Rudy story. But it was kind of a proud, weird way. It was a proud moment for me that Norman High was, students just didn't do that stuff. This is a screenshot from a Silent Help video from yesterday. So if you didn't quite get, you want to see it again, this is because incline planes are so important. So this is like the last shot, but this shows you step by step, and it's like a 3-minute video. I'm going to go ahead and show this. I'm afraid I'm going to worry about copyright here. Okay, so I'm going to turn the recorder off, but so don't get copyright issues, but I will put this in the link below. It's only a minute long. Okay, so I'll pause recording. Okay, so this came in the mail, email, yesterday, or was it the day before? Anyway, it's my limited liability. Whereas the articles of the organization of Ask Me Learning LLC and Oklahoma Limited Liability Company. How about that? So now I am official, and that's why I could buy the table and the chair last night, because I can write it off. So this is my company, and you'll be seeing more of this in the weeks to come as we are preparing for June. And would love to have you join us. Now, someone asked about this. I said, well, is it nonprofit? And yes, that was the idea originally, is to go nonprofit. That was always what we wanted to do. I spent 2 weeks trying to go nonprofit. And let me tell you, the U.S. government is not too keen on you being nonprofit because they don't get the money. You get to write it all off. So you can do it, but it kind of costs you around $2,000 right off the bat just to get all the lawyers involved and all the paperwork. So this cost me $100. So I said, okay, what we're going to do is we're going to become a company this year, and we'll establish ourselves this summer, fall, spring, and then in fall of 2022, we're going to open up a non-profit company, and that its whole sole purpose is to give students scholarships to do this, to take our courses, because part of our mission is to go for those kids that don't have any opportunity, that don't have physics in their district, that don't have advanced biology or advanced. Most small schools don't go past Spanish 2, but Miss Pippins will be with us, and she'll be teaching Spanish 3, Spanish 4. So all the stuff we're going to do, one of the main incentives was to get to kids who don't normally get these kind of opportunities. So we obviously need to be able to make them, we'll offer deals for now, but then eventually we'll have a scholarship available. So it is going to be nonprofit eventually. But also to have a nonprofit, you better make it simple. Ours is way too complicated, and it would have been a pain. But if you keep it simple, we're doing one thing. Actually, we're doing 2 things. We're also going to give money to you guys. Like if you're trying to go, like right now, the district doesn't pay anything for people like we just, for instance, we have 6 girls or 5 girls that are like really good at wrestling. I mean, Norman High is one of the best high schools of women's wrestling in the country. So they get to go to nationals in Fargo, North Dakota. Well, guess what? They got to pay for everything, like $600-700. The girls got to come up with the money, and the district isn't putting a dime. They don't. The district doesn't pay hardly any of that. And I'm not blaming the district. They just don't have the money. So we're going to do and part of our nonprofit will be raising money as well to pay for academic contests, robotics contests, even girls wrestling, things that don't get funded. The Palm squad gets no money to go to Florida for nationals, no money. They have to raise it all themselves. So we would be partly doing that as well. All right, back to physics. So this was our Thursday stargazing, 661 I gave them between 1 and 4 stamps. So remember, you all will be turning in 6.6. We're still a little ways away from that. It'll be probably the end of next week because we still got more work to do on 6.6. I was saying 6.4. It wasn't. I was also saying 6.4. I don't know. I got to decide whether it's one or the other. I'm not going to do both. You'll submit either 6.4 or 6.6. So yeah, I don't know yet. They're both important. Actually, 6.6 is, to tell you the truth, a lot more important than 6.4. 6.6 is the second most important sheet. Okay, in the packet. 6.1 is the most important. Meet table 4. Anybody want to get met today? I'll turn this thing off. I'll stop recording and we can meet one of you. We've met a few of you. Okay, we're back to recording. So we had a meet and greet there. And let's go back now. We've promised we're going to do some physics here. Okay. All right. So today's physics. Now your homework is back on 6.4 to do number 2. And that's, you may have already done it, but that's just to keep up. I imagine 6.4, you will turn it in because I told you we're going to turn it in. Now the question is, would you turn in 6.6? Would you submit that? But 6.4, just so I'm not lying to you, let's go ahead and say you turn it in. But it'll be next week sometime because we're going to slowly get through it. So just do number 2 if you haven't already, and then you're still caught up with the class. Yesterday, we talked about inclined planes, and what I didn't really send you, I can't send you guys the board, but I think probably a number of you, when you first did the inclined plane, you did it this way. That's 75% of students do that when they first, I'm sure I probably did in college, because you're thinking that you've been ingrained in your head that the normal force is up, right? But in reality, normal means perpendicular. So the normal force is always perpendicular to the surface. So if you go ahead and tilt your axis, then it's easy. The normal force is the y-axis. When you tilt your axis, we don't do it just to be difficult. We make it life easier because if I hadn't tilted the axis, I would have had 3 vectors at an angle. And the mg is the one that wouldn't have been at an angle. But when I did tilt the axis, now I only have 1 vector at an angle. That's the mg. So I went from having to do 3 cosine sines to 1 cosine sine. So that's why we tilt the axis, is to make our life easier. Oh, and I went around today and gave a stamp for number 1. So that was something you're supposed to do last night. I gave 1 to 4 stamps for that one and probably had 50%. That did it. Okay, now I think I can show this one without having to, because this is mine. I'm not going to offer copyright. So I'm going to show this, and then I'll skip forward, but let me show this one. Yeah. 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 Okay. So let me find it here. I know I should be more prepared. Hold on. Daggone it. Okay. Hold on. Maybe I won't show it. It's in the on the comments there, but for some reason I think I killed it earlier accidentally. Oh, it's bad. Oh well, I get all that back later. All right, no, let's save us time. Not worry about it. It's unless that's it. Nope. Okay. So it is it talks about, I did kill it. That's so stupid. It talks about using head to tail on inclined planes. I can show you the main. There's a screenshot from it. and it's just me kind of talking over it. So this is the last screenshot of it. So it's probably worth your watching. We watched it in class. I don't normally show these in class, but it's a 4-minute, I call it scratch off physics. I had the problem all done, and then I kind of unerase things as I go. But I'm going step by step how to go through the process. And this is the first time that we would go, we would go right to the head to tail on an inclined plane. So let me get this out the way here. All right, so this thing. So you're going from, so if I do a head to tail diagnosis on these 4 forces, the N, the MG, the FP, and the FK, I'm trying to solve for FP. Then if I add these up head to tail, the summation of forces ends up going down the incline, and that's what you want. You're saying you're trying to pull this thing down the incline. You had to do a little bit of kinematics to find the acceleration. And then this, if you go watch this, it's from last night's, but I'll probably put it in there again in the comments. If you'll watch this 4-minute video, you'll get what I was going to try and show you anyway. And then talk you through it. But this is the approach you take. Huge part of test 6B will be inclined planes. And then the whole point of the head to tail diagnosis is to see if I'm getting the lengths right. Because when I draw them in a free body diagram, I'm kind of guesstimating, well, that's that long. So, the N is this N here. This is not, one of the questions I asked the class, this is not congruent to that, right? What's it congruent to? This is false.
It's the component that's parallel
Right.
to it.
So this is true. Thank you. That's true. It is congruent to that. It's not congruent to this because that represents all the forces in the tilted y direction. So it's congruent to the component of that mg. All right. So hopefully that made sense. And all the forces in the y direction cancel. Okay. I had the kids do a panoramic view of the rooms because we're going to put that in our banner at the top of our website. A panoramic view of the 807. Okay, so now let's talk about why we're here today. And finally getting into it here at 1:43. So why are we here today? We're here to start thinking like Einstein. Like I told you at the very first, I said Einstein's born around 1880s, and that's when the elevator was first invented. So it was the new modern, only the richest and only the most expensive buildings had them. And so it was a real privilege. You had an elevator. People would not get inside a elevator. Absolutely not, because they thought it was like some kind of magic box that would transport them, and the door opens and they freaked. You go into the first floor and you're standing there talking, and the door opens, the 4th floor. What is this magic? Let's burn some witch or something. So that freaked everyone out. So they had to put a person in the elevator to kind of, the elevator operator was born because people would not go in there by themselves. So that's how freaky it was to everybody. But elevators and physicists have this real connection because an elevator is a box that you can turn into a non-inertial frame of reference. Now, let's talk about a non-inertial frame of reference. All right. So draw this in your cheat notes. Non-inertial frame of reference. Okay, so first off, let's talk about an inertial frame of reference. An inertial frame of reference is the room you're sitting in, or in Rose's case, her backyard. That's her inertial or your inertial frame of reference. Mine is this room I'm sitting in. Everything in this room this room itself is not accelerating relative to the street outside. Rose's backyard is not accelerating relative to her front yard. So everything is in a non-inertial frame of reference. Okay, so non-inertial means the whole daggone thing's accelerating. So best shown by an example. Let's say that June comes around and you read On the Road with Jack Kerouac, and you said, okay, I'm going to hitchhike. Don't do this. You say you're a senior and you're graduating, and you say, what am I going to do with my life? Oh, I'm going to hitchhike out to California. So you think, well, maybe I'll just take a train, just jump on a train. And so let's say that you see a train in Norman and it's a freight train. And so it's sitting on the tracks. It's stuck, you know how they do sometimes. And so you go and you get into that train, that boxcar. And here you are, you lay in there for a while, you get tired, you fall asleep. Here you are asleep. Okay. Then you notice though, when you fell asleep, you looked up on the ceiling and somebody had a string and a ball attached to it, and it was hanging down like you'd expect. Okay, so you see that. Now you're sleeping soundly. The train, unbeknownst to you, the train starts to accelerate. There's a force that caused the train to accelerate. You wake up and that ball that was hanging from the ceiling is now hanging like this. Now, let's say you don't realize, you've been asleep, so you don't realize, then you shut the door trying to hide. So you didn't realize the train was accelerating. If you saw that, what would you think? If you didn't know the train was accelerating, you would think it's a ghost. Okay? There's some kind of ghost in this boxcar that's making that thing do that, some paranormal. But in reality, it's because the train, see, the thing is, non-inertial frame of reference, it's a non-inertial frame of reference to you because you don't realize that the frame of reference you're sitting in, the boxcar, is accelerating to my left as I'm looking at this. If you are going to go drive around to this afternoon, hang something from the, if you maybe people have seniors have stuff, so hang some dice or something from the rear view mirror. And then as you're driving, once the light turns green, you press on the gas and watch that thing. It always curls back. Whatever this is, the direction of motion is always the force, the acceleration is always this way. Once you've reached your speed in your car, what will that thing do? Once you've reached the speed you're trying to get to.
Wouldn't it go back down?
Yeah, it goes back down. Like this ball, and then you fall back asleep, you're freaking out, and then you get all scared, but you fall back asleep, and then you wake up and the ball's back like that. That's because now you're no longer accelerating, you're going at a constant speed. When you can't feel velocity. You can't, we're all going now, but because the earth's rotating and all, but you can't feel velocity. You can feel acceleration, but you don't feel velocity. Like for instance, you could play ping pong on a train. If the train's going at a constant rate, you can play ping pong, right? This thing in this boxcar is going to keep just hanging there. And then at that point, it's an inertial frame of reference. When it's going at a constant velocity, it's an inertial frame of reference. When the whole thing speeds up or slows down, it's a non-inertial frame of reference. Okay. So you go back and forth. What freaks people out is when they don't realize they're accelerating. And that's what freaked them out about elevators. So in an elevator, you're standing here, and once you hit the up button, once it starts to accelerate, an elevator then becomes a non-inertial frame of reference for you in the elevator. Okay. So let's say, and we've done this, and I'm going to give you points if you'll do it. So there's your elevator. let's say you're standing on your elevator, you're standing in the elevator, you get on there, there's a scale right here. This is a scale. How much time? I got 10 minutes. Okay. And on, let's say you weigh, look, we're looking at, right now we're looking at 6.6.4 is the reference sheet there. And so in 4A, it says that your weight is 490 newtons. That's what the scale says. The elevator's not moving. And by the way, we've done this at the Vista. We've done it at Sarkey's. We've done it at the Embassy Suites. I need somebody to go to Devon Tower and do this. You got now the scale has got, it's got to be an analog. This has to be an analog scale, meaning that it's not digital. Most scales now are digital, but you can still find those with a needle. Okay, it has a needle. If yours has a needle, you know, that rotates, then you have an analog scale. So I want you to film yourself. First, get on the elevator at Devon, and that goes to like the 50th floor, you know, because it goes up to that restaurant. Although I warn you, you need to dress nicely. I tried to do it with just my shorts. My wife and I had been out and said, okay, I'm going to go check this out. They wouldn't let me on the elevator because of my shorts. I was discriminated against for being casual. Anyway, so I couldn't get on. But you all, if when you go there, maybe this weekend or next weekend, take some friends along and then take a scale and dress nice. Tell me you're doing it for physics. So first thing you do is you film yourself. Now this person filming themselves, they weighed 490 newtons. All right. Now you push the up button and see what happens to the scale. Most people gain about 20 pounds. And you felt that. You've all been in an elevator. You push that up button, and for just a half a second, you feel, it's actually 1.4 seconds, somewhere in there. You feel heavy. Okay. Otis has a certain guidelines. You can't be accelerated too long. People get sick. So just sitting there, standing there on before you turn the thing on, you have a mg. Okay. That's your true weight. And you have the normal from the scale. Normal. Okay. I'll put S. Normal from the scale. This is what it's measuring, the normal from the scale. And so, you know, sitting in the elevator, nothing's moving. You have N minus mg equals ma, which is not moving, so equals 0. That equals 0. And so normal force equals mg. And that's what you expect when you stand on a scale. You expect it to give your weight. But if you hit the up button, all of a sudden we have N minus mg equals ma, because you are accelerating. Your body's accelerating, right? You don't want to accelerate. Newton's first law, a body at rest stays at rest. You want to stay at rest. Let's just say you have inertia. What I'm trying to say in one word is you have inertia. You're going to resist anytime somebody tries to move you around. So this is actually called the elevator equation. You'll find a book. Now, normally you don't see it in that form. I'll show you, huh? You'll see it more like this. Here's your standard elevator equation. So there's the N at the top. There's the N minus mg equals ma. That's if you're accelerating either up or down. And so you solve for N, mg plus ma. You normally pull the m out. And so this, I'll give you a chance to write that down. This will be on the next or the one after. It's either on side 16 or 17 of your equation sheets. But the scale reading is what your apparent weight is. That's not really your weight. That's how much contact you're having. Your mass, of course, that doesn't change. G, that's Earth's gravity, that doesn't change. And then the acceleration is for the elevator. Now, it's either positive on your way up or it's negative on your way down when you're accelerating. So it's because conceptually, it's because your body is staying still and the the elevator is forcing your body to accelerate, and therefore you are resisting, and that what you're measuring is your weight plus your resistance. Okay, comes from. So that's why, like me, when I do it on an elevator, I gain 20 pounds. So I go from 200 to 220 pounds when I hit the up button. Okay. What happens when I get to the floor? Say it's Embassy Suite. Say I get to the 6th floor. What happens as I get to that 6th floor and the elevator stops? What happens to my scale reading then?
Would it decrease back to your original
Yeah.
weight?
So wait. Hold it now. You said back to, okay. I weigh 200 pounds before the elevator goes anywhere. I hit the up button. I jump to 220, but only for 1.4 seconds or somewhere in there, 1.1. We've timed this thing, not for very long. And then once the elevator reaches its constant speed, then how do I feel? If an elevator is going at a constant rate and you're in the elevator, do you know you're in the elevator? Do you know you're rising?
No.
You do not. Your body cannot feel velocity. You can only feel acceleration. Now, once you hit, so my scale went from 200 to 220 in 1.4 seconds. I'm back to 200, and then I stay at 200, 2nd floor, 3rd floor, 4th floor, 5th floor, 6th floor. What happens in that 1.4 seconds that I go from rising to stopping? What happens to my weight now? Now, what's it go down to?
Would it go down to 0?
Nope. Then in that case, I would float. It go down, and we'll get to that later. Now you're thinking like Einstein. It goes down to 180. I went from 200 to 220 on the way up. Once I got to that, now my body's saying, okay, my body says, I want to keep rising the rest of my life. I never want the body, for some reason, says, I don't want to stop rising. And then what does the elevator do? At the between the 5th and 6th floor, it falls out from under you as it now you're saying, no, I'm not going to stop. And it's saying, well, I am. And so that 20, I lose 20 pounds. I become light on there and if it had stopped immediately, then I would float. I would fly in the air. I'd hit the ceiling actually, because my body just keeps on going up at whatever, 20 miles an hour, whatever the elevator is going up at. So yeah, now we're thinking like Einstein. All right, so this is a little introduction. I wanted to at least get that elevator equation to you, and then we'll work some problems on it. You can probably solve now. You can probably finish 4, but we're going to take this way beyond that. We're going to talk about Einstein. I don't get much chance to talk about like relativity and some of the cool stuff of physics because this year is COVID and all. But we'll talk a little elevators tomorrow, and then how the genius of Einstein, and I'll show a little clip from a movie of him for his happiest thought, and then we'll get into what this has to do with curvature of space-time. Okay, so that's tomorrow. All right, we cool? Anybody? If you guys are, don't forget the homework. There is number, what was it? Number 4. No, 4. You can finish up 4, but it was actually number 2 on 6.4. All right, so go ahead and you guys can take off if you want. If you stick around, and we'll talk to you if you have something to say.
I didn't answer your email, but I think like I'll come in to take the 6B test on the 25th.
Okay. I will be there. Let me turn off the recording here, but I will be there. Stop.